Hey guys, in this video we're going to look at how pH and equilibrium is affected whenever you have a situation where you have a common ion. So consider that we have 0.10 molar acetic acid. So the base reaction is acetic acid and water is going to be at equilibrium with acetate ions and the hydronium ions, which would generally have a pH of around 2.87. Now, what's going to happen to the pH if we add sodium acetate? So, sodium acetate will produce sodium ions and acetate ions. So it will add a product in the acid dissociation reaction. So it'll add those acetate ions, forcing equilibrium to shift to the left. Whenever equilibrium shifts to the left, the hydronium ion concentration will decrease because it's moving away from that product side. Well, if hydronium decreases, pH will increase. It will become more basic. So here you notice we have a pH probe in a solution of the 0.1 molar acetic acid solution that's at about 2.9. But as soon as we add that sodium acetate, the pH is now at about 4.7. So here's some problems that we'll come across using the common ion effect. It wants to know what's the pH of a 0.3 molar acid solution, and then the pH of the solution that contains 0.3 molar of the acid and 0.52 molar of a salt containing that anion. So let's first look at how you would find the pH of that acid. Remember, this is a weak acid, so it is one of our equilibrium problems that we come across. So here would be the dissociation equation. We have the acid and water produces the hydronium ions and the anion. It told us that our initial molarity of the acid was 0.30 and we had none of the ions. We would decrease the amount on our acid of our reactant side and increase the amount that we have on our product side. And that we would plug into a Ka equation. So we would have the Ka of the acid, which is 1.8 times 10 to the negative fourth, is equal to x squared over the 0.13, since we can ignore x in that case. If we solve for x, we get that the hydronium or hydrogen ion concentration is 7.3 times 10 to the negative third, which if we plug in for pH, the negative log of that number will equal about 2.13. Now, here's how this changes if it's in the solution with that common ion. So here we have the pH of the solution that contains 0.3 molar of our acid and 0.52 molar of the salt with the acid ion. We still have our same dissociation equation, but if you look at our initial amount, we have 0.30 molar of the acid and 0.52 molar of the anion, but still none of the hydronium. We still have that 0 under hydronium, so we still have to add to our product side and subtract from our reactant side. So then we have our equilibrium amounts that we have to plug into that same Ka equation. But because we started off with some of the anion, our Ka equation is still the same Ka value, but we now have 0.52 times x over the 0.30. So whenever we rearrange to solve for x, so multiply by the 0.3 and then divide by the 0.52, we get that X is equal to 1.0 times 10 to the negative fourth molar, which is going to give us a pH of about 3.84. So the pH did indeed go up because equilibrium was shifted more towards the left. We did not produce as much of the ions as we did in the original equation where it was only the acid present. One way that you can solve problems like this whenever we have common ions and you're finding the pH is to use the Henderson-Hasselbalch equation. This is an equation that is on your reference sheet. It's just being able to use it. So if you have a solution that contains significant amounts of an acid-base pair, so the acid and its conjugate base or the base and its conjugate acid. So here's an example reaction just like we did before, where we have the weak acid and then its conjugate base. You can use the Henderson-Hasselbalch equation. So how they found the Henderson-Hasselbalch equation, which is listed below, is that the pH is equal to the pKa plus the log of the base over the acid. So that's going to be the base ion, so the anion, over the acid concentration. They derived this from the equation for Ka and solved it for that H+. So they simply rearranged it, and then since we're solving for pH, which is the negative log, they took the negative log of everything, which allows it to become its normal form. So in this equation, you can use this equation if you're looking for pH, if you're looking for Ka, if you're looking for the concentration of the acid or the base. You'll just fill in whichever variable you do not know. And in general, if the X is very small, you can pretty much ignore it. It doesn't really matter in the Henderson-Hasselbalch equation if that X value is really small. So here's an example of what this was going to look like. I want to know what's the pH of a solution containing 0.3 molar of the acid and 0.52 molar of our salt with the anions. So this is the same problem that we just did. Note that the 0.30 molar is for our acid, so the 0.52 molar is for our conjugate base. And using the Henderson-Hasselbalch equation, we know Ka, we know the amount of base and the amount of acid. So we can plug those values in. But remember, the P is the negative log. So pKa is negative log of the Ka, which was 1.8 times 10 to the negative fourth, plus the log of the base concentration, the 0.52, over the acid concentration, the 0.3. And when you plug that in, it gives you a pH of 3.98, which is the same thing we got using the ICE table, but with less work. When you're able to use the Henderson-Hasselbalch equation, is whenever the initial acid or base is not super dilute. So if it's like 0.00004, that probably wouldn't be appropriate to use Henderson-Hasselbalch. We rarely have situations like that. You also want to use the Henderson-Hasselbalch whenever the K is fairly small. So you really want concentrations of at least 10 to the second or 10 to the third larger than K. We'll hopefully have some examples we can use with this whenever we get back, but let's look at another problem. Here it wants to know what's the pH of a solution if we have 0.12 molar lactic acid and 0.1 molar sodium lactate. And the Ka for lactic acid is 1.4 times 10 to the negative fourth. So yet again, make sure that you're aware of what is going in as your acid, what is going in as your base. So our pH is going to be equal to our pKa, so the negative log of the Ka, which is the 1.4 times 10 to the negative fourth, plus the log of the base, so the lactate ion, which is going to be 0.10, over our acid, which is going to be the 0.12. So this would be our initial setup when we plug everything in. And when you punch that in the calculator, you get a pH of about 3.77. You could solve this with an ice table, and you will get the exact same amount. I solved it with an ice table on my paper, and I got a pH of 3.78. So very similar, but this requires a little bit less work. Let's look at another situation you can deal with Henderson-Hasselbalch. You can also look at the number of moles that you're starting with your acid and base instead of initial molarities. So if you don't know molarities, you can simply plug in moles. But it's still going to be the pH is equal to the pKa plus the log of the moles of the base over the moles of the acid. And this is only allowed where you can use the value of moles when you're using the Henderson-Hasselbalch equation. You cannot plug in moles into Ka and Kb, only if you're doing it for the Henderson-Hasselbalch equation. There are a couple example problems in the study review checklist, and I'll try to host some open hours pretty soon to address any questions.